In this video, I'm going to show the image of why we need to watch out for the noise in a SerDes system. From Electronics 101, we will know the noise exists in a circuit inside a passive resistor or active transistor or any PN junction. Those noise are unbounded, which means the statistic characteristic should be evaluated, such as the mean and standard deviation sigma values. The larger noise amplitude occurs at a longer waiting time or larger amount of data in the outlier distribution. Therefore, the sigma value is related to the bit array requirement. Again, the bit array is the total error divided by the total number of samples. So, the lower bit array requires a greater number of samples or longer waiting time. For example, for bit array equals 1e-12, the ±7 sigma peak noise amplitude should be taken with the mean Gaussian noise in a lean budget estimation. Similarly, the bit array equals 1e-15 should take ±8 sigma peak noise amplitude. Does that make sense to everybody? Here, for the random noise in a CMOS process, the thermal noise may be from the resistors and MOSFET, and the flicker noise is from the MOSFET. Lastly, the shunt noise occurs at any PN junction. Can you think of any random image which degrades the signal-to-noise ratio SNR? Correct, DC offset, and we discussed this in the why DC offset cancellation video. The difference is that the random mismatch here causes different DC offset between secant parts, but it's still statistic characteristic. For example, some parts may have a big DC offset, and some might not. Similarly, to observe the outlier DC offset in an extreme case, the number of samples must be sufficiently big to achieve a reasonable confidence level. Therefore, with a limited run of Monte Carlo mismatch simulation, a 1 sigma value is necessary to extrapolate the yields or worst case for extensive amounts of samples. For example, if the parts per million ppm yield is the target, the worst case peak DC offset or mismatch must be calculated from a ±6 sigma extrapolate number. Let's pause the statistic noise and move to the deterministic noise. From the SerDes image, are any deterministic noise image? Think about the SerDes image one more time for 5 seconds. Good. Channel or median. In the Y equation video, the channel's bandwidth could be limited while the SerDes speed is pushed higher and higher, or low-cost channel is needed. Therefore, the intersymbol interference RSI distortion, because of the big channel loss or narrow 3 dB bandwidth, would distort the signals and get a cross-eye diagram. Therefore, people may treat the RSI as another kind of noise in a deterministic form. Hopefully, the RSI is bounded and can be mitigated with a few equation techniques in our equation videos. Besides the RSI, do you have any other channel images related to the deterministic noise? Right, reflection. We haven't discussed the impedance match, but you may have some ideas from Microwave 101. If not, bear with me, and I would like to make another video later to discuss it further. The instant signal will reflect partially if the impedance does not match. Therefore, the plot of maximum power transfer to the load versus the receiver load would have a peak power transferring, which means there is no reflected power under a low matching condition. On the other hand, with the impedance mismatch, the received signal power is less, and that would degrade the SNR due to the destroyed signal power. Even though the reflection is a distortion, it sometimes treated as a deterministic noise. Hopefully, this may explain why the impedance match is necessary at the high-speed SerDes. Back to the distortion. Any idea of the side effect of the reflection image? Think about your channel images for 5 seconds. Bingo! Crosstalk. Any big capacitance between the two lines will create a coupling path due to the low impedance path for high-frequency signals. Adding the impedance mismatch causes the reflection signals at the TX output, and then TX reflected signal will couple to the arcs due to the low impedance path. If the TX aggressor and the victim eyes are on the same side of the median, we call it near-lane crosstalk. On the other hand, if the TX aggressor and the victim eyes are on the different side of the median, we call it far-end crosstalk. Lastly, no matter which kind of crosstalk, the termination would be added to achieve the impedance matching such that both reflection signals and crosstalk can be reduced. In addition, proper design with the last coupled capacitance path in the on-chip, package, socket, and PCB channels is a must. Please be advised, the capacitive coupling is just an intuitive image for your reference here, and the inductive coupling could be another crosstalk source if inductor coils exist. Besides the high-speed signals, what else could be the noise source? Correct. The power supply could be another noise source. Sometimes the SerDes supply could be tied to other circuitry like the digital core logic, which will introduce the extra supply noise into the SerDes. If possible, the supply of the high-speed SerDes must be delicate to avoid any supply noise crosstalk. On the other hand, the high-speed SerDes itself would have lots of switching activities. Therefore, the SerDes self-introduced supply noise causes the data-dependent noise as well. To mitigate self-introduced supply noise, the supply impedance must be as low as possible. For example, perform a solid power ground grid on chip routing and add enough bypass capacitors around it. In addition, the free-chip BGA package will further reduce the supply impedance compared to other wire-bound packages. Hopefully, we've covered most kinds of noise here, but to be clear, noise in a circuit could be voltage or current quantity, even though we only talk about the voltage noise here. Since most SerDes circuitry take voltage quantity, let's start with the signal image of voltage versus time as a case study here. If a vertical voltage noise is added around the signal transition, the horizontal timing uncertainty or jitter in time is generated by the voltage noise. In design practice, the jitter could be reduced if the voltage noise is minimized. Hopefully, you can see the relationship between the vertical noise and horizontal jitter images are tied to each other. For the relationship image, what can you do to reduce the jitter further? Correct. Increasing the slew rate as sharp as possible in the transition image. As you can see, a fast slew rate will lead to a less jitter or timing uncertainty with the same voltage noise. Simple math show you T is V divided by M, and a bigger slope M will lead to a smaller jitter T under the same voltage V. Therefore, speed up the any transition time in a critical data or clock path is a must. Here is the summarized image you may have for why we need to watch out for the noise in a series system. The goal is simply to reduce the bit array by increasing the signal-to-noise ratio SNR. Since the random noise is unbounded, we must increase the signal power and decrease the random noise as much as we can, be based on the outlier noise requirement. To avoid extra determinist noise or jitter to further degrade the bit array, a few extra design practices must be made here. First, the DC offset cancellation is necessary to minimize the decision offset. Second, the equalization circuitry must remove the ISI from the limited bandwidth channel and implement an impedance match properly. Third, the crosstalk or interference must be minimized by minimizing the coupling mechanism carefully in any capacitive or inductive path. Fourth, the supply noise must be as clean as possible by a dedicated series supply at very low supply impedance implementations. Lastly, the jitter must be minimized by a circuit noise reduction and speed up the transition time of any critical clock or data path. Hopefully, those noise images will tell you why you need to take care of the noise seriously in your high-speed series design under a very low bit array requirement. Thanks for watching. Before you go, if you benefit from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share a video link with people who may be benefiting from it.